Okay, this week we're going to be talking about correlation, and in this first part, we'll be reviewing Pearson correlation. In the second part, we'll be talking about Spearman's rho, and then in the third part, we'll be talking about the chi-square test for association. So recall Pearson correlation is used to determine the strength and direction of the linear relationship between two continuous variables. An example could be looking at the correlation between salary and age, assuming that as age goes up, the salary also goes up. The value of Pearson's correlation ranges from -1, which is a perfect negative relationship, to +1, which would be a perfect positive relationship. A value of 0 indicates no linear relationship between the two variables. There still could be a different kind of relationship between the variables, say curvilinear or logarithmic, but again, the 0 just denotes no linear relationship. And we use little r to denote a Pearson correlation. All right, what are our assumptions to be able to use a Pearson correlation? First and foremost, as I already said, both variables are measured on a continuous scale, and this could be interval or ratio. The variables are also paired. So what do I mean by this? Each case or individual has the value for each variable. For example, each person would have an age and a corresponding salary. We assume linearity in that a linear relationship exists between the two variables. And here we can use a scatter plot to visually estimate if that linear relationship exists. There should be no significant outliers, especially if you have a small data set. And again, we can use a scatter plot or a box plot to visually look at possible significant outliers. And then last, we have a normality assumption in that the data comes from normal distributions. And here we can use skewness and kurtosis to look at normality, but we can also use the Shapiro-Wilk test for normality. All right, so establishing if a linear relationship exists, notice in the two scatter plots on the left, we see that we either have a linear increasing relationship or a linear decreasing relationship. In both of these scatter plots, it's telling us that a Pearson correlation would be appropriate. However, in the two scatter plots on the right, we see two nonlinear relationships, one being more exponential and the other one being curvilinear or parabolic. And in these situations, the scatter plot is telling us that a Pearson correlation, which again gives the strength and direction of a linear relationship, would not be appropriate for these two scatter plots. All right, what about significant outliers? Take a look at the scatter plots on the left, and we see a black dot that is far away from the rest of the data. Pearson's correlation is particularly sensitive to outliers, especially the smaller the data set you have. So what are our options when we have a significant outlier? And we kind of talked about this last week. One is we can keep the outlier or outliers, especially if we have a large data set. We can also Winsorize or transform the data. Winsorize, remember, it involves removing that outlier and replacing it with the maximum or minimum of the data set that exists once that outlier has been removed. We can transform our data, which sometimes helps with multiple outliers. So maybe taking the exponential or logarithmic value of all of our data points. That's one option. And then, you'll hear people say, oh, well, you can remove the outlier. Again, this is highly controversial, especially if you have a small data set. All right, what about checking for normality? So again, I mentioned skewness, kurtosis, and the Shapiro-Wilk test. First, let's talk about skewness. Skewness describes the shift of the distribution away from a normal distribution. All right, so it's when we pick up a left tail or a right tail. So negative skewness shows that the mode moves to the right, giving us a tail on the left. And then positive skewness shifts the mode to the left, giving us a tail on the right. Kurtosis describes how heavy or light the tails of the distribution are. So positive kurtosis is an increase in the sharpness of the distribution or the peak of the distribution. And so we get heavy or longer tails. Whereas negative kurtosis exhibits a flatter distribution with light or shorter tails. And then lastly, the Shapiro-Wilk test, which is actually under correlation, under an assumptions option. This is used to assess if the data is significantly different from a normal distribution. And the test results in a W statistic or value, where small values indicate your sample is probably not normally distributed. All right, how are you going to interpret how small is too small? The test is going to give you a p-value, and when that p-value is less than alpha or 0.05, it's going to indicate rejection of the null hypothesis that the population is normally distributed. So if you see a really small p-value for your Shapiro-Wilk test, like less than 0.001, that's going to tell you that your data is not normally distributed. And again, if it's not normally distributed, then the Pearson correlation is not appropriate. All right, so let's work on an example, and I'm going to, I am going to pull up JASP. Okay, I have pulled up ELS data in JASP. And the first thing we want to do is explore a relationship between math achievement scores and math self-efficacy. So let's go into descriptives and let's put our base year math self-efficacy in and our base year math achievement in. All right, and we want to look at skewness and kurtosis. And let's also go under, so we want to go under statistics and we want to check skewness and kurtosis. I'm going to go ahead and check Shapiro-Wilk to show you something that happens. And then in customizable, let's check a scatter plot and change our add regression line to linear from smooth. All right, and there we go. It takes just a minute because this is such a large data set. Okay, so here we have our descriptive statistics and we have our scatter plot. I can go back to PowerPoint where I've put the image. And so first we can look at the scatter plot and this blue line of best fit, which is showing us that we do have a linearity assumption here. I know it's a little bit hard to see because we have so many data points, all right? But we do have a linearity assumption. We also don't see any really obvious outliers. And again, this is such a large data set that we're not too particularly concerned about outliers here. And then lastly, with normality, first let's look at the skewness and kurtosis values for our two variables. So with skewness for math achievement, we see negative 0.06, and with kurtosis, we see negative 0.5. So we're seeing a little bit of left skewness, negative skewness, and we're also seeing a little bit of negative kurtosis, but these values are pretty close to zero. And then similarly with math self-efficacy, we see some positive skewness of 0.184 and a little bit of negative kurtosis of negative 0.827. But again, we're not too worried about these values. We would be able to assume normality by looking at them. Shapiro-Wilk, notice we do not get Shapiro-Wilk here in our descriptives. And the reason is in JASP, it only calculates Shapiro-Wilk when your data set is between 3 and 5,000. So just a problem with this extremely large data set. All right, but now let's run the actual correlation. So we want to go into regression and classical correlation. And again, we want to put in our math achievement and our math self-efficacy. All right, and again, we know we can leave it here on Pearson's R because we have linearity and normality and no significant outliers. We want to check also flag significant correlations. And we can do a scatter plot again, so you really can look at your all of your assumptions in correlation, because also in assumption check you have multivariate and pairwise normality. And again, just showing you that here it's telling us, okay, I can't run Shapiro-Wilk because your sample size is too large. All right, but we do get our correlation here, and let's go over back to, I'm going to go back to PowerPoint, and we see here we get a significant correlation of 0.386 between math self-efficacy and math achievement. All right, what is this telling us in terms of sample size? So remember that we can interpret Pearson's R as an effect size, where less than 0.1 is trivial, 0.1 to 0.3 would be small, 0.3 to 0.5 is moderate, and anything larger than 0.5 would be considered a large effect. So here we have 0.386, which would be a moderate effect. And we see that p-value is less than 0.001. So we can say here that there's a moderate positive correlation between math self-efficacy and math achievement, and we would report that R and p-value. All right, so just to go through reporting the results as we start thinking about APA format and the paper at the end of the semester. So here we could say, using L's 2002 data, a Pearson correlation was run to assess the relationship between math self-efficacy and math achievement in 10,443 ninth graders. Preliminary analyses showed the relationship to be linear, with both variables normally distributed as assessed by skewness and kurtosis, and there were no outliers. There was a statistically significant, moderate positive correlation between math self-efficacy and math achievement. So again, just reporting then that Pearson R and the appropriate p-value. What would you have said if the p-value had been greater than 0.05? So if the results had been non-significant? Well, just making up some numbers, we could then say there was no statistically significant correlation between math self-efficacy and math achievement, and again, reporting that Pearson R and the non-significant p-value.